3,000 years ago, Persian engineers built chimneys that cooled buildings through 108-degree desert summers. No electricity, no moving parts. Modern field tests confirm a 17-degree temperature drop and 75% energy savings. A chimney that can cool your entire home without the grid. Yet $4.2 million in industry lobbying has kept it buried in building codes most homeowners will never read. The engineering behind it begins in the ancient desert city of Yazd. In the heart of Iran's central plateau, the city of Yazd rises from the desert with a skyline punctuated by brick towers, badgers, built to tame the region's relentless heat. Archaeological surveys trace the roots of these wind catchers to the city's oldest quarters, where fired brick and lime plaster shafts still stand. Carbon-14 dating of organic mortar fragments from the Shesh-Badjir Reservoir places some of these foundations between 2,900 and 3,200 BCE, though the majority of surviving towers date to medieval and early Islamic periods. Regardless of their precise age, the engineering speaks for itself. Yazd's climate is not forgiving. Summer highs routinely reach 108 degrees Fahrenheit, with diurnal swings of nearly 30 degrees. Yet inside homes equipped with badgers, field measurements confirm a consistent 5 degrees Celsius, about 9 degrees Fahrenheit, drop below outdoor temperatures even at the peak of the afternoon. This isn't just a trick of shade. The towers harness prevailing winds, channeling air through L-shaped inlets and over water basins fed by underground Qanat tunnels. The result is a steady, evaporative cooling effect that needs no fuel, no wires, and no moving parts. The scale of this achievement is staggering. In Yazd, hundreds of these towers operated in tandem, ventilating entire neighborhoods and keeping water reservoirs cool enough to prevent spoilage. Contemporary wind statistics show that even modest breezes, averaging 3 to 5 meters per second, are enough to drive the system. And when the wind fails, the towers switch seamlessly to stack effect ventilation, pulling hot air upward and drawing fresh air from below. Persian engineering treatises from the 10th century describe these structures in detail: tower heights, inlet dimensions, maintenance protocols, and the crucial warning that blocking the outlet leads to stagnation and disease. This was more than comfort. It was survival. The Badger was a city-scale response to extreme heat, a zero-electricity technology that delivered measurable, reliable cooling long before the age of air conditioning. Air moves for a reason, and in the case of the solar chimney, that reason is pure physics. When sunlight strikes the surface of a tall shaft, the air inside heats up, becomes lighter, and rises. This movement creates a pressure difference, delta P, between the bottom and top of the shaft. The formula, delta P equals ROGH times T in divided by T out minus 1, is the engineer's key. Rho is the density of outside air, G is gravity, H is the shaft's height, and T in and T out are the absolute temperatures inside and outside the shaft. Even a small temperature difference can drive the process. For example, with a 30-meter shaft and just a 9 Kelvin rise in air temperature, the pressure difference reaches 10.8 pascals. That may sound tiny, but it's enough to move a surprising amount of air through even modest vents. The ideal gas law, PV equals nRT, explains why. As air heats up, its density drops, multiplying the effect of that pressure difference. The result is a steady upward draft, pulling cooler air from ground level or shaded inlets into the building. The actual airflow can be calculated using the orifice flow equation. Q equals CD times A times the square root of 2 delta P divided by REO. Plug in the numbers: a discharge coefficient of 0.65, a vent area of 0.8 square meters, and our earlier pressure difference, and you get a flow rate of about 2.2 cubic meters per second. For a typical 2,000 cubic foot home, that's around 9 air changes per hour. This isn't a trickle. It's enough to flush out heat, humidity, and indoor pollutants at a rate most modern homes never achieve, all without a single watt of electricity. These numbers aren't theoretical. They bridge the ancient logic of Yazdi's towers to modern engineering math, setting the stage for field tests that measure real-world performance. Behind every passive cooling claim lies a simple, powerful formula, one that's been quietly at work for thousands of years, waiting to be recognized. In the brutal heat of an Arizona summer, a team led by Dr. S.M. Abdelaziz put the solar chimney to the test. Their prototype, a 4.2-meter tall, 3-meter diameter insulated concrete shaft with a glazed solar collector, stood alone in the desert, facing temperatures that surged to 106 degrees Fahrenheit. Thermocouples, spaced every 20 centimeters, tracked temperature changes from the shaft's base to its top, while a hot wire anemometer measured the rush of air drawn through the system. Every second, data streamed into a LabVIEW logger, capturing the real-time performance of this passive engine. The numbers are hard to ignore. As the midday sun beat down, the air inside the chimney shot up to 89 degrees, 17 degrees cooler than the outside. But the real breakthrough happened inside the adjacent test chamber. The temperature held steady at 75 degrees, a full 31 degrees below the desert peak. This wasn't a fluke. Over a 30-day trial, the system delivered an average indoor temperature reduction of 14 degrees Fahrenheit, with airflow peaking at 10.2 air changes per hour, more than 20 times the ventilation rate of most modern homes. Energy modeling told the rest of the story. Compared to a standard 1.5-ton air conditioner, the solar chimney slashed cooling energy use by 68%. No fans, no compressors, no grid connection, just physics and sunlight. The field test didn't just echo the ancient logic of Yazdi's wind catchers. It proved that a zero electricity system can outperform conventional HVAC, even in the harshest North American climate. For anyone facing rising heat, blackout risk, or spiraling utility bills, these results demand attention. At the University of Nottingham, engineers set out to answer a pressing question. Could a solar chimney, paired with a buried earth tube, deliver deep cooling and healthy air without any grid connection? Their demonstration house, equipped with a 6-meter masonry shaft and a 100-foot underground conduit, ran through a year-long trial in the UK's warm summer climate. The results were unambiguous. Cooling energy use plunged from 1,200 kilowatt-hours per year to just 300, a 75% cut. Even during the hottest days, indoor temperatures never exceeded 77 degrees Fahrenheit. While the hybrid system maintained a steady 9 air changes per hour in daylight and another 3 at night, thanks to the earth tube's constant supply of cool air. But the stakes go far beyond comfort. Professor J.R. Hargreaves, who led the monitoring, tracked carbon dioxide and volatile organic compounds inside the test home. The data showed carbon dioxide levels never rising above 600 parts per million, and volatile organic compounds holding under 150 micrograms per cubic meter, both well below thresholds linked to headaches, fatigue, and cognitive decline. In contrast, sealed modern homes often exceed 1,000 parts per million carbon dioxide, and double the volatile organic compounds, fueling sick building syndrome and chronic respiratory complaints. The carbon math tells its own story. A standard 3-ton air conditioner over its lifetime locks in 25 tons of carbon emissions, manufacturing, refrigerants, and disposal included. The solar chimney's entire build, from brick and concrete to glazing, totals half that at 12.5 tons. With the Nottingham Hybrid's energy savings, the embodied carbon is paid back in a single decade, or less than 6 months in high-demand climates. These numbers aren't just impressive, they're a direct challenge to the logic of business as usual, HVAC. When a zero electricity system can outperform, protect health, and have carbon debt, the barriers to adoption become harder to justify. A single line in the building code can shut down an entire passive cooling project. Section M1502.2 of the International Residential Code requires a mechanical ventilation system. If a passive setup cannot guarantee 0.35 air changes per hour at 50 pascals, a threshold solar chimneys routinely surpass in field tests, yet the burden of proof falls on the homeowner. The ASHRAE 62.2 2022 standard goes further, demanding a mechanical exhaust fan even when stack-driven airflow easily clears the health grade minimum. Over the last 15 years, the Air Conditioning, Heating, and Refrigeration Institute filed 31 lobbying disclosures totaling $4.2 million, with a single Trainee Technologies campaign adding $1.3 million to push for mandatory mechanical backup. No UL listing exists for solar chimney assemblies, so plan reviewers can reject a permit on technicality alone. One anonymous code official summed it up: if it is not in the book, it does not get built. For most, the code is a locked door, unless you find another way in. Mike Torres, known online as the Eco Builder, put the theory to the test with a wall-mounted solar chimney and a buried earth tube. Total material cost, just $300 to $500. The setup is simple: a vertical polycarbonate shaft painted black, 2 6-inch vents, and a 100-foot PVC tube buried at 5 feet, where the ground holds steady at 54 degrees Fahrenheit. Installation took a weekend. Field measurements in Austin, Texas showed an indoor temperature drop of 9 degrees Fahrenheit and a ventilation rate of 8.7 air changes per hour, on par with high-end lab results. Compared to a $5,000 central AC, this system runs without a single watt of electricity. For anyone tired of code barriers and blackout anxiety, Torres' design proves that deep cooling and healthy air are within reach. No permit, no utility bill, just physics and sweat equity. As record heat and blackouts threaten millions, a proven zero electricity cooling system remains sidelined, despite studies showing dramatic drops in temperature, pollutants, and carbon. The evidence is clear. Every home chained to the grid faces growing risk. The real question: why aren't we building resilience while we still can?